I don't know if you'll over
there and I broke yeah. It's just like with my second day ski. We spent like $1,000, so because I was just one of my times.
Okay, so usually my students are better at this problem than me. This one makes me confused because I don't know why the negative numbers throw me off. So when I do this problem, I usually make a number line for myself. And so I say, okay, if it's below the melting point, what's the phase? Yeah, solid, frozen. So if it's less than this, then it's going to be a solid. Okay, if it's between this number and negative 85.1, then it's going to be what? If it's between melting and boiling, it'll be a liquid. And if it's above 85 or negative 85.1, then it's going to be a gas. Okay, so then we just have to go through, and these are the temperatures that they gave us. And we have to pick the correct phase. And then remember, this one has the pictures. You have to make sure the picture looks correct. So what would the phase be for negative 145? Where should that fit? That should be a solid. Okay. And then I just want to remind you that, so this molecule was HCl. So you need to make sure the HCl has a bond between it. Some of them will have alternating atoms, and they're really beautiful, and they're alternating, but they're not bonded. So if it's not the molecule HCl, then that's wrong. So make sure you pick the right. It has to be a molecule. So something like they're touching, they're bonded, and then solid means that it has to be really ordered. So I have HCl, and it's really ordered. So something like that would be a solid. Okay, how about this one? Negative 103. What phase would that be? What phase would we look for? Yep. This one would be a liquid. And then the picture that represents that needs to have these molecules. They have to be molecules, so don't pick individual atoms. And they have to be HCl. And they have to be like pretty close to each other, kind of disordered, kind of like sliding past each other. But they still have to be molecules. They still have to be bonded together. Does that make sense? And then what would this one be? This one would be a gas. And then for that, our molecules are still, the atoms are still in a molecule. They're not broken apart. We can't have atoms separate or it's not HCl. And then they just need to be spread apart from each other, kind of disordered, not touching. Okay, so that's something that will be on the final, something like that. Questions on that one? You guys feel pretty good about that one? Okay, that's great. Okay, we are going to continue with chapter 7 today. We talked about maybe doing a lab, but I ran out of time to set it up. I think we talked about that last time. So we're going to first go to our slides. Let me see if I can. Oops, wrong one. Let me pull over my slide and my Alex. So last time, we talk about oil clock, the piston problem? Do you remember last time? Let's look at this one and see. Then we need to go over another example of this. Or are we good on that?
What did you say?
Did we do Boyle's law last time? I think that's kind of everything. Yeah, we can do another one. Okay. So this is our piston problem. Boyle's law. Let me find. Okay, so let's use that chart again. I think that's pretty helpful on the where we're trying to figure out what's changing. So we have pressure can change, volume, number of particles, and the temperature. And these are all related. And then what we're going to do is we're going to look at initial values that we have, final values that we have, and then what we expect to happen. So is the other thing going to go up or down? And we're going to use our intuition. Hopefully we're building our intuition on how these relate. So this one says a cylinder is filled with 10 liters of gas. So that's telling us one of these values. What's this? 10 liters. Oops.
Volume.
That is a volume. That's our initial volume. So we start at 10.0 liters. Okay. The initial pressure of the gas is 294 kilopascals. So that's the initial pressure. So I'm going to put that in that box. 294 kilopascals. Okay. The piston is pulled up, expanding the gas until the gas has a final volume of 23 liters. So that's my final volume. 23 liters. So we didn't change the amount of particles in there. We didn't add, it doesn't say we added, oh, and then we added gas. So N is the same. And it doesn't say anything about the temperature. So we're going to assume that the temperature doesn't change. Okay. So then let's think about what's happening in a syringe. So what happened to the volume? The volume went up. So if we increase the volume and we have the same amount of gas, what should happen to the pressure? It should decrease. So if our pressure, so this number, the number that we find here should decrease. So we're going to take our pressure and then we're going to use these two numbers to get a smaller number. So what ratio of these numbers gives us a smaller value? 10 on the top. Over 23.0 liters. So liters cancels, and then we should get a smaller volume. Or pressure, excuse me, pressure. Okay, let's use our calculator. Plug those in. So 294 times 10 divided by 23. So that gives me this number. If I go back to all of the numbers they gave me are 3 sig figs, so this number should have 3 sig figs in my answer. So 128 decimal kilopascals. Also, well, yeah, liters pascal. Okay. So we talked about that one last time. Okay, is that one okay? All right. Let's do, the next one I want to do is called Charles' Law. Before we do Charles' Law, I want to watch a video. Let's find it. So we're going to watch this video after this ad. Wait a minute. Okay, so this is a physics professor at Utah State, and he's going to do a demo for us. So he's going to dip the balloon into the liquid nitrogen. What do you think is going to happen? So we have a balloon that's going to shrivel. Anyone else have a guess? You think that's going to happen? Okay, so the pressure is the same. Pressure is staying the same. Number of moles of gas is staying the same. He filled it up. The particles aren't changing. So pressure and N are staying the same. We're looking at how is the volume and the temperature related. Okay. All right. Let's see. Let's see if your prediction is correct. Okay, so hopefully that's helping us with our intuition on what happens when we change the temperature. So this is the balloon problem. So this is what we're going to do for the balloon. So we have a balloon. It's in a shed. And it starts with, this is our volume. So remember, volume is in liters. So that's our initial volume. We start with 36.6 liters. Okay. I don't know how my computer's doing. The temperature inside the shed is 9 degrees Celsius. So that's our initial temperature. But when we do this problem, our temperature needs to be in Kelvin. So do you remember the equation to get our temperature into Kelvin? That's the first thing we're going to do. Do you remember it? Yes, plus 270 something. Yes, so Kelvin equals Celsius plus 273.15. That's our. This is not an Alex, so you either have to memorize that or you have to write it on a note card for the test, because you will need that for the test. Okay, so I'm going to take my 9 degrees plus 273.15. What's that? What's 3 plus 9? 20, 15, 12. So 80. So tell me if this sounds right. 282.15. Okay, then we have to remember our rules for sig figs when we're adding. So this one has no sig figs, or decimals, excuse me, no decimals. So we can keep no decimals. So this will be our, no decimals. This will be our answer.
So do we erase the 9?
Yes, so I'm going to erase that 9. And we have 3 sig figs in our temperature. I probably should figure out what's going on. So 282 Kelvin. Okay, that's our initial temperature. All right. Then we take the balloon outside and the temperature is negative 19. So we're going to take that one and change it again. So we're going to say negative 19 degrees Celsius plus 273.15. This one also has 0 decimal places. So if we add these together, I'm not going to do that in my head. I'm sure some of you can do that in your head. Negative 19 plus 273.15. I should figure out what that is. Sorry. Okay. Oh, this seems wrong. What am I doing? Undo. Oh, I didn't add. Kelvin can't be negative, so that seems wrong. Okay, there we go. So our temperature here is 254 decimal place Kelvin. Because our number didn't start with any decimal places, then our answer can't have any decimal places because we're adding. Okay, so the number of moles, so N, the number of particles in the balloon doesn't change. So after we fill it, it stays the same. So that's going to stay the same. And the pressure, it tells us right here, the atmosphere, it's the atmospheric pressure, it's exactly 1 atmosphere. So pressure is not changing. So we just have to decide what's going to happen to the volume based on what happened to the temperature. So we saw the temperature, what had happened here? It decreased, it went down. So then based on the video, if the temperature of the balloon goes down, what happens to the volume of the balloon? It should also go down. So this answer needs to be a smaller value. So we're going to take this number that we started with, the initial volume, 36.6 liters, and then we're going to make it go down with these 2 numbers. So which number do we have to put on the top to make the liters go down? A smaller number, 254 point nothing. Okay, and the bigger number will go on the top. Kelvin, our units drop out and we end up with liters. So let me find my calculator. 36.6 times 254 divided by 282. And all of our numbers after we convert it to Kelvin have 3 significant figures. So this one will have 3 significant figures. This one's tricky because it looks like we start with, this one looks like it starts with 2 decimal places, but it's not in Kelvin. You need to check the sig figs after it's in Kelvin, after we've added the 273. So everything here has 3 sig figs, so we're going to put, let's see, oh, this one's tricky too, 30, we're going to round that up, 33.0. We have a 9 here, so this one will round the 9 up. That bumps this up. Okay. All right, should we do another one? Okay, let's do another balloon problem. Yeah, so balloon, Arctic weather balloon. Okay, let me update our table. So our values could be P, V, number of moles, temperature. And then we have our initial values, our final values, and then what we expect to happen. Okay, very beautiful. Oh, that's D. Okay, so this one says Arctic weather balloon filled with 6.86 liters of helium. So that's our volume. Liters is volume. With helium inside a shed. The temperature inside the shed is 10 degrees. So let's not put 10 here. Let's put 273.15 plus 10. That will give us our answer in Kelvin. That's what we need. So that one's easy. 283. Remember, this one has no decimals, so our answer can't have any decimals. That's why now we have 3 sig figs. So I'm going to put that here. 283 Kelvin. Okay. And then the balloon's taken outside and the temperature goes down. So we're seeing the temperature is going down. So we're going to do 273.15 minus 13 plus a negative 13 degrees. That will give us our temperature in Kelvin. So that's going to be 260, I think. Okay, so temperature is now 260 Kelvin. No decimal places. So 3 sig figs. So now, again, number of moles, so number of particles doesn't change. The pressure stays the same. So the only thing that's going to change is the volume. If our temperature goes down, just like that person at USU, if your temperature goes down, then the volume should also go down. So we're going to start with our volume. Let's see, 6.86 liters. And then we're going to multiply that by these numbers. And we just said if the temperature goes down, then we're going to put the smaller value on the top of this fraction and the bigger value on the bottom. And we'll end up with liters.
Is it always, the temperature always decrease in this?
On this problem, I checked through quite a few, and one time it stayed the same. And every other time it went down.
Right.
So if it stays the same, what should happen to your volume? Yeah, it would stay the same. It wouldn't change. Yep. So be ready just in case it goes up, but if it's an Arctic weather balloon, hopefully your prep shed is warmer than the Arctic. So I don't know 100% that it always is less, but it seems like yes, it is. It seems like that's true. Divided by 283. Okay, so then let's see. Did that go down? Yes, that went down, and then we should have 3 sig figs. 6.30 liters is our volume. Okay. Is that one okay? Okay. All right. Okay, let's go. The next one I wanted to do is using Avogadro's law. This one's a little different. This one, we're not going to use the table. This one's just using the chemical equation that we get. and we have to balance it. So do you remember how if we had, maybe let's do the chemical equation and then we'll talk about it. So this says carbon disulfide gas. So they're going to start making you know everything. So based on the formula, based on what they tell you, you have to know we have to be able to set up the equation. So if we have carbon disulfide, how many sulfides or how many sulfurs do we have? Yep, so CS2. So it says carbon disulfide gas and oxygen gas. So hopefully now you know if they say oxygen gas, what should you write?
O2.
O2. Good. So anytime, so I know oxygen gas comes up, hydrogen gas comes up, chlorine gas comes up. So any of those dark green elements on the periodic table, if they're telling you fluorine gas, hydrogen gas, any of those, they're diatomic. They always come as a pair. And now you have to know that. They're expecting you to just have learned that. So make sure you know that. React to form sulfur dioxide. So what should we put here? So 1 sulfur and 2 oxygens. Good. So make sure, maybe review your prefixes because some of those come up in this problem. And carbon dioxide gas. I'm not going to write the phase because I don't have to turn in my equation, but in the labs, you should always write the phase if it's gas. These are all gases, or solid or liquid. Okay, so let's look at this. The first thing that we need to do is to balance it. So I have carbon, sulfur, oxygen, carbon, sulfur, oxygen. We've got 1 carbon, 2 sulfurs, 2 oxygens. I already have 2 oxygens over here. Oh, I have 4 oxygens over here. 1 sulfur and 1 carbon. So let's see. Let's balance oxygen last because it's by itself. That one's going to be easy to fix. So, but I do need 2 sulfur, so I'm going to put a 2 over here. That's going to mess up the oxygen. To fix the sulfur, now I have 4 oxygens and 2 oxygens. That's 6 oxygens, I think. Okay. So the only thing I need to balance is oxygen now. Let's go back over here. If I put a 3 here, 3 times 2, that gives me 6. Okay, so now everything should be balanced with those 2 coefficients that we've added in the front. So now we are used to saying if I have 1 mole of carbon disulfide, I should get out 2 moles of SO2. So we are used to doing moles to moles. This is the same thing, but with liters. If it's a gas, then we can use the coefficients to figure out how much we should produce or how much we need to start with. So this says what volume of carbon dioxide, so we're looking for liters of CO2. That's what we're looking for. Would be produced by this reaction if we start with 9.75 milliliters, if 9.75 milliliters of carbon disulfide were consumed. So I'm going to write down the number they give me first. So 9.75 milliliters of carbon disulfide. Oh, so this is going to be milliliters. And then I need to use the ratio of these coefficients to tell me if I use up this much, how much CO2. So the ratio here, this one is a straightforward one. This is saying if I don't have a coefficient, that's just 1, right? This is saying for every 1 milliliter of carbon disulfide, I get 1 milliliter of carbon dioxide. And that's what they're looking for, right? Carbon dioxide. Okay, so this is a 1-to-1, so we should be able to just know that this should be 9.75. We can also set this up. So we're going to use our ratio. We have milliliters of CO2. So this is for every 1 milliliter of CO2. I'm getting that from my coefficient from the equation. I need 1 milliliter of CS2, carbon disulfide. So milliliters of carbon disulfide cancel and we'll get milliliters of CO2, which is what they're asking us. So 9.75 times 1 is 9.75. So as long as it's a gas, we can use the molar ratios because of this ideal gas relationship. And that has 3, so our answer should have 3. It also is asking for units. This problem asks for units, so I'm just going to put the unit that I started with, milliliters. Okay. Questions on that one? So this one's kind of like chapter 5. Okay, should we do another one? Okay, let's do one more. Okay. All right, fluorine gas and water vapor react to form hydrogen fluoride gas and oxygen. So what should we put here? Fluorine gas, what's the equation? Yep, F2. F2 plus water, we know water, gives us hydrogen fluoride.
HF.
Yep, HF. And oxygen gas, or oxygen, O2, good. So make sure you're starting to pick up on that. It's not going to tell you the formulas anymore. You need to know, fluorine gas is F2. Okay, I think we got that. What volume of hydrogen fluoride would be produced? Oh, first we need to balance it. Sorry, I forgot that part. So we've got fluorine, hydrogen, oxygen, fluorine, hydrogen, oxygen. So here we've got 2 fluorines, 2 hydrogens, 1 oxygen, 1 fluorine, 1 hydrogen, 2 oxygens. So let's balance. We need at least 2 of these fluorines. 2. Okay, let's see. We have 2 oxygens and 1 oxygen. So let's make this a half. So half times this oxygen gives me 1. But I can't have a fraction, so then I'll go back through and multiply everything by 2. So I'm going to put a 2 here, 2 here, a 4 here, and then this is going to get, that'll just have a 1. Okay, we're okay? It's balanced? Okay, we can also check this has 4 fluorines, 4 hydrogens, 2 oxygens, 4 fluorines, 4 hydrogens, 2 oxygens, so that's balanced. Okay, so now we can answer their question, what volume of hydrogen fluoride would be produced? So we're looking for, and they give us, so centimeters cubed is a volume. What volume of hydrogen fluoride would be produced by this reaction if 2.78 centimeters cubed were of fluorine gas were consumed? So then we need to use these ratios. So we have about 2 centimeters cubed of fluorine. So I'm going to put that on the bottom to cancel it out. I need the coefficient for HF. So 2.78 times 4 divided by 2, or 2.78 times 2, if I simplify that. 5.56 centimeters cubed. And this one again, this one will ask for a unit. Centimeters cubed is the volume. Okay, questions on that one? Okay, so that one's, I think that one's kind of like chapter 5. All right, that was Avogadro's law. Let's see, where are we? Okay, let's look at the ideal equation of state 1. There's quite a lot of these, and some of them are tricky. So this one, we need to use the ideal gas law. Have we talked about that? Not sure? Okay, so for this one, they call it the ideal equation of state. Mostly I've heard it called the ideal gas law. And we've kind of been using this. So that's this relationship between pressure, volume, number of moles, this gas constant, and temperature. So pressure P is pressure. When we do this, ideal gas law, pressure needs to be in atmospheres. Volume is V. When we use this equation, we need volume to be in liters. N is number of moles. We can think of that as number of particles. That needs to be in moles. Sometimes they'll give us that in millimoles, so we just have to make sure our units are matching up. R is the ideal gas constant. We'll come back to this one. Oops, I'm going to put constant with a G. That doesn't make sense. And T is the temperature. And temperature has to be in Kelvin. So remember, if we need it in Kelvin, we're going to do 273.15 plus Celsius. Okay, so one way to know the correct units is to go to your Alex calculator. Yeah. And then if you look at the pi button, you can find the ideal gas constant. There's two. We're using this one, liters, atmospheres, moles, Kelvin. That makes more sense for us. We are not using the one with energy. That's not ours. So make sure you're looking here. And this will tell you, oh yeah, I need my volume to be in liters. I need my pressure to be in atmospheres. I need my N, number of moles, to be in moles. And I need the temperature to be in Kelvin. So that's a good way to check if you can't remember, oh, what was my pressure supposed to be in? You can look at the gas constant, okay? This is the gas constant. So R, that's R. Did I leave some space? I'm going to write R again. R is 0.0820574. And then the units on that are liters times atmospheres over moles times Kelvin. And the reason why we need to make sure that our units are correct is because this ideal gas constant is for these units.
It's on the bottom of it.
Moles times Kelvin. Oh, sorry. So you can actually look up lots of different gas constants to match the units of your problem, but this is the only one that Alex gives us, so we're going to change all of our numbers to match this constant. But know that if you're in another class, you can look up on the internet, you can find different gas constants that match the units that you started with. Okay. All right, so there's quite a number of different, does everyone have this down? Can I erase? Okay, there's lots of different types of this problem. So what we're gonna do is this is gonna be an algebra problem. We're gonna have all of these values and we just have to solve for one of them, okay? So we're gonna get lots of knowns and have one unknown and then solve for the unknown. So this one says dinitrogen difluoride. So what's that? Dinitrogen is 2 nitrogens, difluoride 2 fluorines. And we have prefixes because it's a covalent compound. Okay, well, that will be important later, not right now. Is collected at 18 degrees Celsius. So they're trying to give us the temperature. Let's write the values over here. So temperature is 18 degrees Celsius. But that needs to be in Kelvin, so we're going to add 273.15. This one has no decimal places, so we'll end up with 3 decimal places, 3 sig figs. So 18 plus 273. So 291. Kelvin, that's our temperature. All right, let's keep reading. In an evacuated flask, I think that means that that's the only thing in there. with a measured volume of 40 liters. So that's our volume. Great. Volume is already in liters. That's what we needed. Okay, let's keep going. When all the gas has been collected, okay. The pressure in the flask is measured to be 0.41 atmospheres. Great, we have the pressure. All right, calculate the mass and the number of moles of dinitrogen difluoride gas that were collected. Round your answer to 3. Well, on the test, you're not going to know how many, so just make sure you're looking at your values. Remember, temperature is, look at the sig figs after you convert it to Kelvin. So temperature right now has 3, this has 3, this has 3. Okay, so if we look back at this ideal gas law, we have pressure, we have volume, we have this gas constant. Oops, I didn't write it down. 0.08 something. We have temperature. We're looking for number of moles. So this is now an algebra problem. How do we solve for N? How do we get N by itself? Yeah, divide by RT, both sides by RT, and that will give us N by itself. So then we're going to plug in everything else. So N is PV over RT. So that is actually P, 0.410 atmospheres. Oh, I'm going to run out of space. Let me put it down here. This is equal to, so pressure, 0.410, that's a 4. I'm going to type in a 9. Atmospheres, volume was 40 liters.
Is N the mass?
N is moles.
So what if I get the mass?
Then you have to use the molar mass of the compound to find mass, or moles. They give you moles, mass. So R is the gas constant. I'm going to find that in Alex. It's like something like this. 1.5 something something something. Okay, R, and then T is 291. Okay, so let's find our calculator. Okay, the other thing I want to do is keep track of my units. So okay, question so far. We're just plugging it in. Okay. 1 times 40. And then, I don't know a better way to do this.
How much of a molar mass do I have to use? Like in the decimals?
Oh, I just would use all of it if it's in your calculator. Or Alex suggests going 2 beyond your sig figs, so I would use 5 sig figs. Okay. Divided by R, gas constant here, times
What's the gas constant?
this number,
But,
291. Okay. All right, question so far. Okay, so we got this number. Let me keep track of units for you. I think that this is something, if you can keep track of units, this is the number of moles. We just found number of moles. 7. Okay, so let's keep track. So we started with atmospheres times liters divided by, our gas constant is liters times atmospheres over moles times Kelvin, and our temperature was in Kelvin. So watch what happens to our units. Oops, okay. So atmosphere on the top, liters on the top, liters on the bottom, atmospheres on the bottom. So these drop out. And then Kelvin on the top here, Kelvin on the bottom here. And then we have, our units are 1 over moles. Okay, can you see where that came from? And so then I have a number over a fraction. So I need to flip my fraction and multiply. So my answer is in moles. So if you get into a harder science class or like an engineering class, if you can keep track of your units, that can help you know if you're doing it right. It can also tell you like what to multiply by each other because you can get the right units. Okay, so this is moles, but it also wants the mass. So let's type this in here. 6, 8, 7. Okay. So we need to convert. Can I erase some of this if I erase like here? Okay. We need to convert moles to grams. Moles needs to go to grams. So if I'm going from moles to grams, I'm going to multiply by the molar mass. Moles times molar mass equals grams. Okay. So what was the molar mass? Do you remember that? How to do that? This was N2F2. You remember that? Okay. So we just add 2 nitrogens and 2 fluorines for this compound. That's the molar mass for this. Okay, so I'm going to just use my full number. So this times N2, so 2 nitrogens plus 2 fluorines. Oh, I have all sorts of weird things happening. So this is my molar mass here, right here. So I have 2 nitrogens, 2 fluorines, and that's going to be multiplied by my number of moles, and that will tell me the mass. So my mass is 45.3 grams. 45.3. Okay, questions on that one? Okay, there are at least 3 different versions of this question. So, do you want to go over another one? Okay. There's one that's like super hard. And the rest are not so bad. Okay, so same thing. We have to figure out what they give us, what we need to find, and then rearrange the ideal gas law so that we have what we need. So our ideal gas law is PV equals nRT. Let's see, reaction between liquid takes place at 12 degrees Celsius, so that's our temperature, plus 273. Is that 285? Okay, Kelvin. So temperature has to be in Kelvin. That's why I did that. In a evacuated vessel with a measured volume, great, we have a volume. The volume is in liters. Oops, degrees Celsius. I'm trying to put a 0 and a degree. So that is, why am I doing that? Liters. 3 sig figs. And the reaction produced 40 grams. So that's mass. We have mass of 46 grams of CO2. So this has to be in moles. So we need to take our mass, divide by molar mass, and that will give us moles, which is the value that we want. Okay, so we're going to find N. R is always the same. We have T, we have volume. We're looking for pressure. So here I'm going to divide by volume, and that will give me the pressure. So first I need to find the number of moles. So I'm going to go to my Alex calculator, and I'm going to take 46, and I'm going to divide it by my molar mass to get moles. And our chemical is carbon with 2 oxygens. So carbon plus 2 oxygens gives me CO2. So 46 divided by this will give me the number of moles. So we have about 1 mole. So 1.0452. Okay. We'll put an extra one. Okay, so let's go through. So we've got pressure is equal to the number of moles that we just found, gas constant, temperature over volume. Pressure is 1.04525 moles times the gas constant, 0.8 something, was it 0.5521, something like that, times the temperature, all over volume. Okay. And then we'll just type that in. So oh, that's perfect. That's on the top already. Moles times gas constant, which is right here, times the temperature, which has 3 sig figs, and then all of this divided by there we go, the volume. Okay, so then this is, what do we find? We found the pressure. Because we use this gas constant, our pressure will be in atmospheres. And we could go through and check all of our units. And then everything we wrote down, our temperature had 3 sig figs. So we're going to round this to 0.489. There's lots of dates right there. Okay, questions? Yes. It says 2. Oh, that's because this has 2. Okay, thank you. Thank you for stopping me. So this one will be 0.49. Okay, thank you. Okay, I should pay attention. Thank you. Okay. Well, we've got 25 minutes. Do you want to do another one of these? Do you want to do another problem?
Is the hard one finding volume?
The hard one is finding temperature. It was like an engineer is finding the operating temperature of a cylinder, and you have to do like 6 steps. That one's really annoying. Okay, what do you feel like doing? So here we are. We've got through this one. So we've got quite a few topics left. Do you want to do another topic? No? Okay. Okay. I'm wondering, so we have 1 class day left for chapter 7. We've taken two chapter 7 days. So I think maybe we should go through another topic if we can. Okay. So let's do this partial pressure one. Some of these are not so bad, but let's do this one. Calculating pressure. Okay, this one's not too bad. So this one, for this, it's a lot of just counting. So we have this one for counting, calculating partial pressure from of a gas. So we have N2 and O2. So this one's just like finding a percentage basically. So mole fraction and partial pressure. So the first thing that I like to do is I like to find the total number of particles. So if we count these, there's a lot. 1, 2, 3, 4, 5. Oh, this is hard for me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I think there's 20. I'm going to count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I think I didn't count that one. 20. Okay, I think there's 20. So the first thing that I need to do is make sure that I'm using the key. So I have nitrogen gas, I have 2 of those. And then I have oxygen gas. If I have 20, then I have 18. So then I just find the fraction. So the mole fraction is, this is representing, I have 2 out of 20 are nitrogen. I have 18 out of 20 are oxygen. So that's pretty easy. Just counting. Yes, you do need to simplify. You look at the pressure they give you. So it's saying this box has a pressure. This is representing some device that has a pressure of 1300 torr. So you're going to find, first you find the mole fraction based on 4 sig figs based on the pressure. So what is 2 divided by 20? Oh. 0.1. So then I need 4 sig figs. How do I get that to have 4 sig figs?
Wait, how did you get 0.1?
2 divided by 20.
Oh, you just,
Yeah, it has to be a decimal. I think that's right. Did I do it right?
we want you. So,
Because I have 2 nitrogens out of 20 total. And then I have 0, 0. That'll give me 4. That's 3, 4, 0, 0, 0. Okay, what's 18 divided by 20? Oh, let's just do this one. 0.9. Okay, other thing, mole fraction should add up to 100. Or not 100, 1.
yeah.
Yeah, so then you can know if you're doing it right by make sure this number, these 2 mole fractions have to add up to 1. Okay, great. So then partial pressure is you just take your mole fraction. So let's fix this. This is multiply the pressure by your mole fraction. So my pressure was something torr up here. 1300.
When we have the pressure, like ATM or atmosphere pressure?
That's okay. Then your answer will be in. See how the box tells me mine's torr? It matches. It should just match. Yep. So my fraction multiplied by the pressure will give me, so it's saying like this fraction of the pressure is coming from the nitrogen. This fraction of the pressure is coming from the oxygen in this tank or whatever.
Yeah.
So I'm going to take this times 0.1 to get my pressure for nitrogen. And then I'm going to take this times my fraction for the, we'll just put pressure for oxygen. So let's do the top one first. 0.1 times 1300. That's 130. Oh, 130. And we need 4 significant figures. So I'm going to put a 0 at the end. And then this one, 0.9 times by 1300 is 100 or 1170 decimal. That also has 4 sig figs. These should also add up to give you the total pressure. So 1170 plus 130 gives me 1300. Yes, that's true. So that's another way to check, make sure you're on the right track. Okay, let's type in these little numbers. Oops, not 1700. 1170. Okay. So that one's not too bad. Okay. I feel better about getting through one more. And we can work on the rest next time. These ones aren't as much math. This one's math. The rest of them are less math. Okay.